two situations in which we assume mutual independence of events involve performing multiple trials of experiments. These fall into two categories. We could be performing identical trials of the same experiment over and over, or we could be performing trials of different but unrelated experiments. So let's look at those two cases. So in this situation, we repeat an experiment. And assume that we have inspected the objects involved so thoroughly that no further observation could change our opinion. So we use this for sort of simple experiments like tossing a coin, rolling dice, choosing a marble from an urn, with replacement, because if we take the marble out and don't put it back, then it's not the same experiment anymore. Or choosing a card from a deck, again with replacement, because if we take the card out and don't put it back, then it's not really the same deck of cards anymore. Now let me repeat. Identical trials means we've inspected the objects so thoroughly that no further observation could change our opinion. That's a very strong assumption. It's a perfectly good assumption if we're playing with toys like a coin or dice or marbles in an urn or a deck of cards. But I don't know how often in life it's really realistic to say, no matter how much we observe these trials, we're not going to learn anything. Most of the time in life, as we're performing trials of whatever we do, we're taking in the information from the outcome of every trial. So this is a very strong simplifying assumption. Perfect for games like this. How perfect it is in different situations in real life, I don't know. So the most basic setup is that the experiment has two outcomes: success and failure. And the probabilities of these are p and 1 minus p. So success could be getting a hit on a coin toss, or it could be rolling a 7 on 2 dice, or it could be choosing the blue marble from an urn with blue and white marbles, or it could be choosing an ace from a deck. Whatever, we decide that there's an outcome that we're going to call success and an outcome that we're going to call failure. So the idea is that we perform this experiment many times, and there's there's at least 4 really natural questions that we could ask about the experiment and the trials. So what's the probability we get at least one success in the first n trials? Another natural question is, for some number k, what's the probability that we get exactly k successes? Another natural question is, we could ask, how long does it take to get the first success? Or in other words, what is the probability that the first success occurs on the kth trial? And another question, what is the probability that we never see a success? So again, little p equals the probability of success. And of course, 1 minus p is the probability of failure. So let's look at question 1. The probability of at least one success in n trials. Well, whenever we see the word at least in a probability problem, it means we could add up probability of exactly one success plus probability of exactly 2 plus probability of exactly 3, but that would be a drag. It's easier to compute 1 minus the probability of 0 successes. So 1 minus the probability that we fail n times. So this is the probability we get anything but n failures, and that's probably the simplest expression for it. That's the probability of getting at least one success. Alright, now let's look at the probability of getting exactly k successes. So this is, well, p is the probability of success, k successes, and then I guess n minus k failures. Now that would be, if I leave this alone, this is the probability that the first k trials are successes and the last n minus k are failures. But of course those k successes could be the last k trials, or they could be mixed up anywhere in the n trials. So we really need to multiply by n choose k. Meaning we choose k of the n trials to be the successes. So this expression is the probability of exactly k successes in the n trials. Alright, now a related question, what's the probability that the first success occurs on some trial? Okay, well this is different from the previous problem because we don't have to worry about where that success happens. It happens on the kth trial. So we get fail, 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 k minus 1 times, and then success once. And that's all there is to it. Now the fourth question, how about if what's the probability we never see success? So this is the probability that we fail, 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 etc. And infinitely many times no success. So I guess I can't really raise it to a power if there's infinitely many fails here. But the best I can do is say, I can raise it to the nth power and say the limit of that as n goes to infinity. Now if 1 minus p is a number between 0 and 1, but not including 1, so if 1 minus p is between 0 and 1, not including 1, then when we raise this number to higher and higher powers, it tends to 0. So I guess that means p is somewhere between 1 and 0, but not 0. Now if p, probability of success, is 0, then I guess the probability of failure, if the probability of success is 1, no, I meant the probability of success is 0, then the probability of failure is 1. And then we certainly succeed, and sorry, I got confused. The probability of success is 0, and the probability of failure is 1, and then we certainly fail, 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 and never see a success. But basically, in most realistic problems, that probability is going to be somewhere between 0 and 1. Not 0, not 1. So no matter how small the probability of success is, if we continue doing the experiment, we would expect to succeed at some point. The probability of failing forever is basically 0. Okay, now let's look at the other scenario I mentioned. That is when we're studying trials of different and unrelated experiments. So the independence assumption can come from performing trials of different unrelated experiments. So for example, so let's say we have components of a circuit, and we'll name them 1 through 4. And let's say they're arranged in parallel. So here are components 1 through 4. Now these are different components, and let's say we have historical data. And after we look at the historical data, we decide that these work with probabilities P1, P2, P3, P4, respectively. And let's say we decide that if one fails, that does absolutely no bearing on the other ones, whether they're going to work or fail. All right, and let's also assume that the circuit works if at least one of the components is working. So any one of them could fail, any two, even three of them could fail. As long as there's one working, then this is still functioning properly. So the question is, what is the probability that the circuit is working? So it's 1 minus the probability that the circuit fails, because we don't want to find the probability that exactly one component's working plus the probability that exactly two components are working plus the probability exactly three. That would be a drag. It's easier to find the probability that none of them are working and subtract from 1. So they work with probabilities P1 through P4, and therefore fail with probabilities 1 minus P1, 1 minus P2, 1 minus P3. So 1 minus P1 times 1 minus P2 times 1 minus P3 times 1 minus P4, because we've judged these things to be functioning independently of each other. Whether one works or fails does not influence our opinion of whether another one works or fails. All right, now let's go back to identical trials and do an example that's a little bit more advanced. Let's roll dice until getting 5 or 7, and we stop. The question is, what is the probability of seeing a 5 before the 7? So we'll either stop the game with a 7, stop the game with the 5. What's the probability that we stop with the 5? We haven't seen any 7s yet. So I'll show you two solutions to the problem. Both give the same number, of course, but there's two different ways to look at it. So this happens if we see a 5 on the first roll, or something that's not a 5 or a 7 and then a 5 on the second roll, or something that's not a 5 and a 7 on 2 rolls and then a 5. So x means not 5 and not 7. Or 3 of those and a 5, etc. So I guess there's infinitely many ways this could happen. So now we need to compute the probabilities of these. So probability of 5 is the number of ways to get a 5, which is we could get 1 and 4, or 2 and 3, or 3 and 2, and 4 and 1. Over a number of ways to roll dice is 36, because we've got 6 things that could happen with the first die, 6 with the second. So 4 over 36 is 1/9. The probability of getting 7 is, let's see, how many ways can we get a 7? 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Over 36. 1, 2, 3, 4, 5, 6 over 36 is 1/6. Then the probability of getting something that's not a 5 or a 7 is 1 minus 1/9 minus 1/6, everything else. So let's see, 9 is 3 times 3, 6 is 2 times 3, so I'm going to need 18, 2 times 3 times 3 for the denominator. So 18 over 18 minus 2 over 18 minus 3 over 18. 18 minus 5 is 13 over 18. So what are the probabilities of these different scenarios? Getting a 5 first is 1/9. Getting something else and then a 5 is 13/18 times 1/9. And then 2 something else is 13/18 squared times 1/9. Or 3 something else is 13/18 cubed times 1/9. If we add these together, that looks like a series that I remember from calculus. It looks like a geometric series. So the probability of the game ending on a 5 is 1/9 plus 13/18 times 1/9 plus 13/18 squared times 1/9 plus 13/18 cubed times 1/9, etc., which is 1/9 times 1 plus 13/18 plus 13/18 squared plus 13/18 cubed, etc. Now there's a nice formula for what happens when you add up all the non-negative powers of 13/18, or any fraction between -1 and 1, not equal to -1, not equal to 1. And that's 1/9, 1 over 1 minus 13/18. So that's 1/9 times 1 over 18/18 minus 13/18 is 5/18, which is 1/9 times 18/5. 18 over 9 is 2. That's 2/5. I guess the fact that this is a little smaller than 1/2 is not too surprising, because there's fewer ways to get 5 than there is to get 7. So I would think it was slightly more likely to see a 7 before a 5 than a 5 before a 7. So I think that makes sense. A little bit less than a half. Alright, so that's one way to look at the problem. Now let's look at a second solution. Let's define events E to be the game ends on a 5, so we see a 5 before the first 7. And let's let F be the event that the first roll is 5. Let's let G be the event that the first roll is 7. And let's let H be the event that the first roll is something else. So not 5 or 7. And we just computed this probability, which I just forgot. 1/9 is the probability of getting a 5 on any roll. And then 1/6 is the probability of getting a 7. And then 13/18 is the probability of getting something else. Now the probability of seeing a 5 with no 7s first is, now since F, G, and H are mutually exclusive, meaning no two of them can happen. Either the first roll can't be a 5 and a 7, or it can't be 5 and not 5 or 7. No two of these can happen. Since these are mutually exclusive and exhaustive, at least one of these has to happen. We're either going to get a 5 or a 7 or neither. We can write probability of E as probability of E and F plus probability of E and G plus probability of E and H. And then each of these products here, each of these intersections, probability of E and F, probability of E and G, etc., can be written as a product using the multiplication rule. So that's product of, I can either say E times probability of F given E, or probability of F times probability of E given F. Since we're looking for E, I think I'll write it the probability of F, probability of E given F way. So the next thing would be probability of G, probability of E given G, plus probability of H, probability of E given H. So probability of F, we said, is 1/9. And the probability that the game ends on a 5, given that the first roll is 5, is 1. Because if the first roll is 5, then we see a 5 before a 7. And the probability of rolling a 7 is 1/6. And the probability of seeing a 5 before a 7, if the first roll is 7, is pretty unlikely. That's 0. If the first roll is 7, then we automatically did not see a 5 before the 7. Then the probability of H, probability of seeing something else is 13/18. And then the probability of seeing a 5 before a 7, given that we rolled something else, is just the probability of seeing a 5 before a 7. Because it's like we started the game all over again. So this is probability of E. So, alright, so we've got probability of E equals a fraction 1/9 plus that. So we can solve for probability of E and see what it turns out to be. So we have probability of E equals 1/9 plus 0 plus 13/18 probability of E, which means if we subtract that from both sides, 18/18 minus 13/18 is 5/18. Probability of E equals 1/9, which means that probability of E equals 1/9 times 18/5. 18 over 9 is 2, so 2/5, which agrees with the answer we got last time. So that's good that we got the same answer, and this video is getting kind of long, so the end.